I'm going to talk about the specific case of self-replicating probes. This is an obsession I've had for many, many years. I'm an engineer, and one of the things that I do is one of the things I'm doing is to try and develop self-replication technology as an engineer. So the running theme I have for this talk is economics. Economics is as universal as mathematics. The subject matter is the rational distribution of scarce resources amongst an excess of consumers. Economics drives biological evolution through natural selection by imposing competition. And in fact, ecologies are in fact economic networks. So self-replication technology minimizes the cost of petaprojects, which an interstellar mission is actually indeed a petaproject. And so the most economic means of exploring the galaxy is actually through self-replicating probes, otherwise known as von Neumann probes. The initial capital cost is of your investment for one or two probes is then amortized over subsequent generations of probes, which you don't actually pay for. And the productivity of these probes grows exponentially. So what we get is, in effect, a trend towards zero specific cost in terms of information return. Now, as an engineer, my working philosophy is much like Richard Feynman. I cannot create, I do not understand. So one of the things that we work on in my group is we're trying to build self-replication technology. And I'll talk a little bit about some of that a little bit later. So let's imagine a self-replicating probe coming towards our own solar system. Now, most technosignatures in this talk, actually apart from Joseph's one, has been focused on astronomical technosignatures. We're going to look at solar system technosignatures. And imagine a self-replicating probe is coming into our own solar system from the outside in. So the first technosignature might be the deceleration of the probe to intercept our own solar system. Now, this could be detectable with a detectability of the order of light years. So this certainly could be detectable from Earth, particularly as the emission of the energy would be pointed towards our solar system to decelerate. The second one might be the Oort cloud. Well, I'm not so convinced about the Oort cloud because the Oort cloud does very little in terms of resource diversity. It's also very far out. You can't take advantage of things like sunlight and so on. A third one might be the solar focus. This is actually quite an interesting one. Potentially, there could be a communications relay located there. It would have to be refueled every so often, but it does imply some kind of inboard transmitter. The fourth technosignature is the Kuiper Edgeworth belt. Yes, certainly there's plenty of potential for fueling, but it's still quite far out as far as what we might regard as the most interesting stuff, which is actually happening in the inner solar system. And the Jovian orbit as well is also an interesting area because this actually is could be potentially where we might want to refuel our sort of like self-replicating machine for subsequent exploration, because the Jovian atmosphere actually has a plentiful supply of helium-3 and deuterium. So, coming up to the sixth technosignature, the asteroid belt. Now, we're going to look into this in a bit more detail because this is actually a much more interesting set of resources for a self-replicating machine. One of the things that we apply is the closure principle. This actually imposes some very, very strict and very, very sort of like constraining possibilities for a self-replicating machine, one of which is built into this idea of self-replication, the closure, is we want to minimize waste and have zero warehousing. Now, one of the assumptions that we work on in trying to build in situ resource utilization of asteroids and the moon is we focused on artificial acid weathering, which is basically a reflection on natural weathering processes, but we use HCl acids and so on, and electrolysis. Now, the main asteroid belt is very stable. Potentially, there could be lurkers hiding around there for a very for the order of 4 billion years. So this would be quite an interesting place to look for, particularly dormant signs of self-replicators or other types of spacecraft. Looking in more detail at some of the resources that we have in asteroids, I'm not going to go into too much detail here. I've spoken about this before. If we look at M-type asteroids, which have a lot of metals, what the techniques we tend to use to extract such metals would be used to convert the metal into a carbonyl. This converts it into a gas. And then we utilize fractional distillation. Now, because this is gaseous, there would be no technosignature of this process. If we look at S-type, again, most of the processes that we get for processing olivine and augite, certainly for olivine, there's no potential technosignature because the processes that we would use could be replicated naturally. Augite is an interesting one because the end product is montmorillonite, which is the main ingredient in bentonite drilling mud. If we did, in fact, find an excess of bentonite drilling mud, this would potentially be a technosignature, but in small amounts, it would not constitute a technosignature. E-type asteroids, and again, this is a natural process. Enstatite is converted to talc, although that's useful as a dry lubricant. It's a natural process. With head, and there's only a couple of examples of this. There's 4 Vesta. Orthoclase it can be converted into kaolinite, which is a clay. Again, this is not actually a technosignature. However, kaolinite is the main, can be converted into porcelain quite easily. This would, in fact, constitute a technosignature. With C-type, and again, sort of most of the processes that we might utilize would not constitute technosignature unless we utilize the resources to convert into plastic, and this would constitute technosignature. With cometary material, again, so like water ice, CO2 ice, and N-ices, there's no real technosignature that we could discern. So as far as the asteroid belt is concerned, any kind of artificial asteroid processing would be very difficult to discern from natural processes or potentially natural processes. Okay, now we'll look at the moon. One of the reasons why I want to focus on the moon is that operating on asteroids is actually very challenging. The milli-G environment imposes some very, very serious challenges from an engineering point of view. The moon has a relatively simple geology, has 5 main minerals, divided into 2 main areas. We have the highlands, which comprise primarily of northite, and the Mare regions, which comprise of other types of material, but from a resource perspective, we're interested in ilmenite. And common to both are olivine and pyroxene. I'll talk a little bit about anorthite in a moment. But this is essentially a source of aluminium. Aluminium is actually a highly multifunctional material, and it constitutes effectively 42% of a spacecraft. So this is things that we've been doing in the lab. We've been taking lunar highland simulant, LHS1, and we've actually extracted aluminium metal and 3D printed it into an aluminium tank to demonstrate the process of taking lunar material and actually extracting something useful out of it. And this is something we're currently developing into a payload at the moment. We're working with a UK company to extract oxygen as well out of lunar simulant. As you notice here, this actually illustrates the kind of processes we're doing. It's a two-stage process. Uh, we have acid leaching using HCl, and we follow that with molten salt electrolysis, which actually yields us our metal. In addition, another potentially interesting resource on the moon is we don't know, but we think there is metal M-type asteroid material buried under beneath the surface of the moon, which would be essential for building a self-replicating machine, where we wouldn't have to actually go to the asteroid belt itself. We could recover this material actually from the moon. And we've actually been doing experiments using this rover that we built for the Canadian Space Agency called CAPVIC. And we fitted it with a boom-mounted magnetometer, drove it around a campus, and we detected various types of substances beneath the surface, as you can see there. So potentially, what we could do is if we could dig beneath the surface of the moon and actually find this metal, we could then extract it and use it for iron, nickel, cobalt. And again, we use the carbonyl process followed by fractional distillation to utilize that for building our self-replicator. So I haven't mentioned, I've talked before about the possibility of building nuclear reactors on the moon using lunar resources. One way we could detect this would be some kind of abnormal depletion of thorium against neodymium and thorium against barium. So this could be readily detectable. This would be a technosignature in itself. And I cite the reference to the Oklo paleo reactor, which was discovered much the same way. So imagine the self-replicator has gone to the moon. It will need to build an infrastructure on the moon in order to reproduce itself. We've been working on the concept of a 10-ton self-replicating module with a 6-month replication time. In only 13 generations, so 6.5 years, it could procreate 1.5 million modules. So this is the power of self-replication. Where would I look? I would look around the rims of the large sort of mare regions, Oceanus Procellarum, Mare Frigoris, and Mare Imbrium, because at these locations we have access to both the highland material and also the mare material, which have different resources. Now, if we have each module has a capacity of 60 tons per year, multiply that out, we actually end up with 90 megatons per year. That's actually exceeds US productivity in steel in 2024. It would also, now I didn't discuss reactors, but essentially a 2 megawatt reactor per module. This generates with 1.5 million modules, 3 terawatts per year. This is actually equivalent to our current electricity usage. And we are classed as a Kardashev 0.73 society. Now, in terms of consumption, we'd be consuming a bit less than 4,000 tons of thorium per year. And actually, this is actually about 10 to the minus 10 of the thorium reserve. So not very much. It'd be very difficult to detect this. And using this productive capacity, we could build the dry mass of a Daedalus starship within a month. We could also build aerobots to then send out to mine the Jupiter's atmosphere for helium-3. And using this self-replication technology, we can manufacture enough fuel to fuel our Daedalus starship in less than 2. We could build the aerobots in less than 2 years and mine Jupiter's atmosphere in 6 months. So now detecting the depletion of helium-3 from Jupiter's atmosphere would be negligible, 10 to the minus 12. So this would be essentially undetectable. And in fact, also with this productive capacity, we could build an O'Neill colony within 160 years. So imagine that a self-replicator has replicated itself. And going back to economics, economics is premised on trade. This is based on Ricardo's theory of comparative advantage. Economics is based on reciprocal exchange, and economic fairness, in fact, is actually a biological concept. The apes and monkeys actually have a concept of fairness in terms of like trade. This is actually a biological capacity rather than a cultural capacity. So I would argue that it's universal. In addition, animal conflicts are asymmetric. If there's a territorial possessor, basically in competition with an interloper, the interloper generally does not invest as much effort as the possessor. So this actually goes against economic theory, this is called the sunk cost fallacy. The tit for tat strategy in game theory starts with cooperation. We can also imagine a berserker scenario where a hostile self-replicating machine basically destroys any potential competition. This is only applicable for any extant ETI, and the likelihood is that there would be no extant ETI. This may be a potentiality. The berserker option in that case would be some kind of biosterilization program, which I don't think is very viable. So I think the cooperation is more likely to be the scenario which we will encounter. So fair trade also requires some kind of non-exploitative extraction, and I've also shown that with the numbers. So imagine a self-replication probe had come to our own solar system eons ago. It found nothing very interesting going on, but there was always the potentiality of the evolution of some kind of intelligent species. So potentially the self-replicating machine could conduct some kind of post hoc trade through the provision of an artifact or a gift as a kind of prototypical contract. So what would that gift constitute? I believe that the greatest gift would be a self-replicating machine itself. This is a unique utility. It involves no cost to the self-replicating probe. Where would it hide it? Well, I think it would be buried to protect it from environmental insults. And the optimal location would be to bury it with M-type asteroid ores. This would provide essentially, it would be invisible to cursory investigation because it would be hidden by the metal deposits, but it would also be accessible through a process of lunar industrialization. This provides a technological threshold. So if that intelligent species then wants to develop its the lunar environment, i.e. us, through the process of industrialization, we would start mining the M-type asteroid material and then open the discovery. So in conclusion, the self-replicating machine, I believe, is the only way to realize interstellar exploration low cost. If we have been visited in the past, then in the process of lunar industrialization, we will find this. And if our encounter with extraterrestrial intelligence will be with AI, not biological intelligence. How am I doing for time?
Time is up, Alex, unfortunately.
Oh, okay, all right.
I thought this was your last slide. I didn't.
No, I just want to mention one thing, and that is that we have a limited temporal window to develop these technologies, because within 50 years, the human race will undergo a population crash. And so post that time, we're likely to become a stagnant society unless we develop self-replication technology and interstellar flight. I'll leave it there. Thank you.